So welcome everyone to the second talk of the A1 homotopy theory lecture series. Today's speaker is Professor Chetan Balwe, and he will be speaking on the A1 homotopy category.
So I'm going to continue my discussion from last time. So last time what we had was a bit of a geodesic to the definition of the A1 homotopy category. So my intention in this lecture is to provide a little bit of intuition behind what is happening, not necessarily to clarify everything, but at least to give some intuition behind it. And in the end, I will give some reading suggestions so that those of you who do want to read more about it will know how to, what to read, so that everything that I have said becomes rigorous in some way. So let's recall the setting. So we have a base scheme S, which is a Noetherian scheme of finite dimension. And then we are looking at the category of smooth schemes over S. So smooth schemes of finite type over S. And these are equipped with the Nisnevich topology. So I had defined it hurriedly last time. I mean, today we will look at it again in some detail, at least to see why it is useful. And then we looked at the category of Nisnevich sheaves on this category, which take values in the category of simplicial sets. So as you may recall, I had defined, simplicial sets, I did give the formal definition of those, but the idea is that it is basically a simplicial set is combinatorial data, which tells you how to put together simplices into a topological space. And then we just forget that forget the topological space part of it and just use the data, which is equivalent to understanding the topological space as far as the algebraic topology is concerned. And in fact, the homotopy, so just like you have a notion of homotopy for topological spaces, you have the same thing for simplicial sets. And if you consider, look at the homotopy category of topological spaces, that is actually, it's equivalent to the homotopy category of simplicial sets. So simplicial sets are basically a combinatorial model for the homotopy category of topological spaces. Anyway, so you may think of these spaces as being Nisnevich sheaves with values in the category of topological spaces, if it helps. But the point, it only causes some technical difficulties, and so to circumvent that, it is easier to work with simplicial sets. So this is a model category, and we use something called the local injective model structure. So I defined that last time. We will not look at the details of that structure because that is not what I want to do. There are many different model structures on this, but as long as you have the same notion of weak equivalences, it shouldn't matter which model structure you're using. Anyway, so the objects of this category is what I will call as spaces. So the point of working with spaces is that when we are localizing with respect to certain morphisms, the category gets complicated, and then it's better to view it as a subcategory of something more general. So some more general objects will occur naturally, and that's why we expand our category to and this is the right category to look at. Okay. So now, if F is a space and U is a smooth category over S, then F of U is a simplicial set. Okay, so normally if we are looking at say just ordinary sheaves, if you so in the context, so for example, any scheme can be viewed as a sheaf over the category of schemes, and then if we do something like this, so if F happens to be a sheaf representing a scheme, then F of U is the set of U valued points of F. And so there it's just a set. Here it has a little more structure. topological space or a simplicial set. And so then we can, whatever we do for simplicial sets, all the algebraic topology that we do for it, for them, can be done here object-wise. So for every object we get a simplicial set, and then we can look at its various invariants, like the homotopy groups or the set of connected components. So this is the first thing that one could look at, that for any u, we look at the pre-sheaf which maps u to pi naught f of u. So pi naught is, so here when I say pi naught, I'm just looking at the pi naught, the connected components of the simplicial set. And so this is just a pre-sheaf. So I mean, that doesn't carry a lot of, well, it does carry information, but I mean, we want to understand, we want to make this, to see the interaction between this algebraic topology along with the geometry below, with the geometry of the category below. So we sheafify this. We take the Nisnevich sheafification. So I mean, okay, so this is the sheafification with respect to the Nisnevich topology. You could do this with pretty much any topology you're using. It's just that in this context, the Nisnevich topology happens to be useful, and we'll see later why. So this is what I will denote by pi naught of f. Okay, so this is actually a sheaf, and I will you can evaluate it on any u in the category of smooth schemes over S. So this is called the sheaf of connected components of f. So far we have not really touched A1 as such, right? A1 has not come into the picture at all. We are not talking about. So the only algebraic topology that is happening because simply we are looking at sheaves in the category, sheaves with values in the category of simplicial sets. And so just like this pi naught can construct higher pi i's. So that is the homotopy groups. Now, when we look at a homotopy group, we need to have a base point. So base point means that inside f of u, we need to pick a point, pick an element. But then, you know, as u varies, this choice should become coherent. So should be, I mean, they should be related. So what you have to do is you pick a u. For every u, you may pick some element x naught of fu, and then for the category smooth schemes over u, you have this pre-sheaf. So v gets mapped to the ith homotopy group of f of v, with the base point being x naught restricted to v. So x naught is a section over u. So you may always restrict it to any scheme that is sitting over u. And then we can construct this pre-sheaf, and then we can look at the sheafification. This is what we will call as pi I of f with pi I of f at the base point x naught. So this is a sheaf over the category of smooth schemes over u. This is a construction that you can do for any u. So this is a fairly big, I mean, so for every u and for every point of that, you have this piece of data. So we don't have just a single group associated to the scheme. I mean, because, well, you could always do something like this. You could pick a global point, right? You could take a section over S, and then that will be a global point. And then you can get a single group sheaf over smooth schemes over S. But you can actually do it more generally. So I'm just saying that there's a lot of, I mean, this is a fairly big construction. But so, okay, so now, once we have this, so what did we use these things for in algebraic topology? So basically, in algebraic topology, as I said last time, we start with the intention of classifying spaces up to homotopy equivalence. Then we come up with the notion of these pi i's, and then the pi i's are meant to be, you know, algebraic tools to detect whether two spaces are homotopy equivalent. It turns out that we fail in this objective because this notion of so two space a morphism is, if it induces an isomorphism on pi i's, it need not necessarily be a homotopy equivalence, except when the spaces are nice. That is when there are CW complexes. Okay, so that's the kind of picture that's going to happen here also. So here we say that F to G is a weak equivalence if and only if, well, this is a theorem. This is not a definition. So we already defined what is a weak equivalence of spaces. A morphism of spaces is a weak equivalence if it is inducing a weak equivalence on stocks, right? At any point, you can take the stock in the Nisnevich sense. And so not in the Zariski topology sense, but there is a notion of stock in the Nisnevich sense, which I had talked about last time. And so then at every stock is basically a simplicial set. And then you look at what is happening on the level of stocks. If that is a weak that's a weak equivalence, then you say that is a weak equivalence of Nisnevich sheaves. And then the result is that this is a morphism is a weak equivalence if and only if the induced morphisms on pi naughts and pi i's, these are isomorphisms. So when I say isomorphism for pi I, I'm talking about going over all u's and all possible points, base points that you may want. This is basically, I mean, this is just tying the picture together. This is not a very deep statement or anything. So these sheaves are going to help you capture the simplicial homotopy type of a space. So I'm saying simplicial homotopy type in the sense that, so what do I mean by simplicial homotopy? What do I mean by homotopy type? So in a model category, you have a notion of weak equivalences, and the idea is to localize with respect to that. And then in the when you go down to the homotopy category, so what is the homotopy type of a space? The homotopy type of a topological space is basically the collection of all spaces which are weakly equivalent to it, right? That is what we mean. So in any model category, we can make sense of such a thing, and so that's what this is. So this is capturing the homotopy type with respect to the simplicial model structure, in the sense that there is another model structure, which is the A1 model structure, which I talked about, which comes about localizing with this model structure with respect to morphisms of the form x cross A1 projected to x, right? So this is just a simplicial thing. This is not touching upon the A1 structure at all. So then, anyway, so the thing is that there is a little more machinery that goes into this, which I had skipped last time. So let me just comment on it a little bit. That this model in this model category, this is what is called a simplicial model category, in the sense that so the morphisms between two simplicial spaces, they don't just form a set. I mean, well, if you just look at it as a category, then of course it is just a set. But then you can create some more structure. You can actually associate a simplicial set to any two objects. So this is basically okay. So this is the. So I'm just writing S for simplicial. Okay, this is a little bit confusing because S was also my smooth scheme, but this S is for, okay, it's for simplicial set. Maybe I should have called it something else, but or maybe put a script S or something. But I hope it is not going to be too confusing. So this is the space of the simplicial set of morphisms from F to G. The n simplices in that are going to be morphisms from F cross delta n to G. So here, what is delta n? So delta n is just a simplicial set, right? It's not a simplicial sheaf. So what do I mean by looking at this morphisms from F cross delta n to G? So delta n gives you defines a constant pre-sheaf, so which maps every u to the simplicial set delta n, and all the restriction maps are just the isomorphisms, are just the identity maps. So this is just a pre-sheaf. And then you take the Nisnevich sheafification of this. So in some sense, this is delta n is just, well, it's the sheafified version of the simplicial set delta n. Then you can look at F cross delta n and look at the maps from F cross delta n to G. So these are the n simplices. So this is a construction that works even in the category of topological spaces. So for example, if you're looking at topological spaces, you can talk about the simplicial set of morphisms from a topological space into a topological space Y. So what are the zero? So if it's a simplicial set, what are its vertices? What are the zero simplices there? They are just the ordinary morphisms, right? The ordinary morphisms, that's just a set. And then what are the one simplices? They are morphisms from X cross delta 1 into Y. So Okay, and then when you look at the two simplices in this simplicial set of morphisms from F to G, so the two simplices are going to be basically well, roughly they are supposed to be like homotopies between homotopies, right? Basically triangles. So you can think of a triangle as a homotopy between homotopies if the one simplices are just the homotopies. So that's the kind of data this this object captures, and so we have this rich object in here. And so if F happens to be HX, so HX is, I hope this is standard notation, that it's the pre-sheaf represented by X, right? So and then we view it as a simplicial sheaf by viewing a set as a discrete simplicial set. So this is a simplicial sheaf. Then we can then what in this case the simplicial set of morphisms from HX to G, it just happens to be G evaluated at X. So this is the so-called simplicial Yoneda lemma that I had mentioned last time. And this is actually how you can view HX as well. We view the category of schemes as somehow sitting inside the category of spaces. So now that we have all this structure, we can talk about things like homotopies and so on. I said that actually we can talk about such things in any category, any model category. But here there is in simplicial model categories, there is a particularly nice way of looking at it. So we can say that two morphisms F and G. Okay, so maybe I should have picked from script F to script G. These are elementarily homotopic. If there is a map H from F cross delta 1 to G, which connects little f and little g in the usual sense. So I didn't write down, the explicit definition because that's too much writing, but you know what I mean, right? So delta 1 has got two vertices. So if you look at what this H is inducing on F cross one vertex, that is going to give you F, little f, and on the other vertex, it's going to give you little g. So then this H is a homotopy from little f to little g. So the thing is that in general, if F and G are just arbitrary simplicial sheaves, this is not necessarily going to be an equivalence relation. So because, I mean, the basic properties are not going to be satisfied. So actually even symmetry will not be satisfied, but yes, symmetry is not satisfied actually. But also more importantly, transitivity will fail. And so you have to basically look at you may want to look at the equivalence relation generated by it, but actually if you take G to be fibrant, then it automatically becomes an equivalence relation. So just let me remind you, like for example, when we were looking at simplicial sets, we saw that if you want to look at maps into the simplicial set, not in the original category of simplicial sets, but in the category in the homotopy category, then it's not, there may be some morphisms in the homotopy category which are not represented by morphisms in the original category. So to really understand morphisms, mapping into your simplicial set in the homotopy category, you have to replace your simplicial set by a Kahn complex, which is the fibrant object in that context. And so it's a similar thing that you have to do here, that if G happens to be fibrant, then any morphism from F to G is in the homotopy category will be represented by a morphism in the original category. And in fact, the set of morphisms in the homotopy category, which I'm denoting by square bracket F comma G, this is equal to the morphisms in the category of simplicial sets modulo the notion of homotopy in this sets. Okay, so basically it's the same picture that we had in the context of simplicial sets, and also we had a variant of this in the category of topological spaces. The same kind of thing is playing out because it is actually the same idea. I mean, that's the reason why we came up with the notion of a model category. So okay, so now let us go back to our objective, which is to talk about the A1 model structure. So the A1 model structure, as I said, so there is a notion of localization for, well, there are multiple notions of localization. There is a certain notion that we are interested in, which is called left goose field localization. Once you do that, what happens is that the objects don't change. The notion of co-fibration doesn't change. It's the notion of fibrations that changes, and the notion of weak equivalences that changes. So how do weak equivalences change? So whatever was already a weak equivalence, it remains a weak equivalence. But then also the projection morphisms of the form F cross A1 to F, where F varies over all spaces, these have been turned into weak equivalences. So of course, just because you added these, maybe some other things will become weak equivalences, because just like when you invert a certain set, maybe it causes some other things to become invertible also. So I mean, we don't necessarily write down a formula for what things have gotten inverted, but I mean, it can be a fairly large and complicated collection, and the whole point of this machinery is to get a handle on that. So anyway, so this is the model. This is the kind of model structure we have, and this model structure has its own fibrant approximation functor. So again, what is the point of the fibrant approximation functor in a model category? It is to understand what are the morphisms coming into your space inside the homotopy category, right? That's the idea. So I mean, one of the things that I hope to do is actually help you. I mean, I will at least give you some intuitive understanding of what this functor LA1 is supposed to be doing. Okay, the explicit construction of it is a different matter, and in fact, it is sort of an infamously complicated things to do any kind of calculations with. But one should at least understand what the intuition behind it is. So let us look at that. So what is this fibrant approximation functor? So this is a functor which goes from the category of spaces to itself. And what it is supposed to do is take any space and look at a fibrant space, which is A1 equivalent to that. Okay, so I will talk about what I mean by A1 equivalence. But so it comes with a natural transformation from the identity functor to LA1, such that for any object F, if you look at this natural transformation and you evaluate it on F, you get a morphism from F to LA1F. So LA1 is what I call as the A1 fibrant approximation of F. And so this morphism is an A1 equivalence. By A1 equivalence, I mean something that is a weak equivalence in the A1 model structure. So as I said, you inverted some things. Some things were already weak equivalences. Now you inverted some other things. And so it is not just these things that were inverted. Because these things were inverted, because the morphisms of the form X cross A1 to X, these were inverted, maybe some other things also became invertible. So all those things that have now become weak equivalences, these are called A1 weak equivalences. So this is an A1 weak equivalence. This is our, so this is one of the properties of this construction. And yeah, so, and of course, LA1F is an A1 fibrant object. So let us see what this does. So I'm just decoding the terms here. So I said these are just the weak equivalences in the A1 model structure. And so A1 fibrant objects, what does it mean? What does that mean? It means that if F and G are simplicial spaces, and if G is A1 fibrant, then the morphisms in the A1 in the homotopy model structure, right? So this is what I'm writing as F comma G in to distinguish it from the similar construction that we did in the context of simplicials of the simplicial model structure. So this is equal to well, you take the morphisms from F to G in the category of spaces, and you go modulo homotopy. So homotopy in the sense of simplicial homotopy that we already talked about. So one thing I should say, and which I have not written here, is that a property of this this left boost field localization is that certainly all the everything that was already a weak equivalence remains a weak equivalence. We add in some more weak equivalences. But what happens to co-fibrations and fibrations is, as I said, co-fibrations remain the same and fibrations change. Just to accommodate the change in the notion of in the injective model structure, every object is co-fibrant. Okay, so in fact, we saw, for example, in the category of simplicial sets, the model structure that I talked about over there was that every simplicial set is already a cofibrant object. So, for example, so this can happen. I mean, it depends on your choice of your model structure. For example, in the model structure on logical spaces, every object was fibrant, but not necessarily cofibrant, right? So there we had to replace the first object. When you're looking at morphisms from X to Y, we have to replace X by something cofibrant, that is a CW complex, right? But when we are working with simplicial sets, and we are looking from morphisms from X to Y, you don't have to do anything to X because X is already cofibrant. It's the Y that you have to change into a Kahn complex. And so that is exactly what is happening here. That see, even back here, when I said, look at morphisms from F to G in the simplicial model structure, I'm not doing anything. I'm not saying anything about F, but I'm saying that G has to be fibrant. This is big because F is already cofibrant. Okay, so that is one of the reasons why this particular model structure is useful. But there are other model structures which are also useful and preferred in some other contexts. So I'm basically following the construction that was followed by Morel and Vygotsky in their foundational paper. So yeah, so this is the basic interpretation of this term, A1 fibrant. This is what it is for, but still let us see what it means further. So in the A1 homotopy category, if I take any scheme X and I look at the projection from X cross A1 to X, this has to become an isomorphism, right? That was the whole point of this exercise, that I want to view X cross X as an isomorphism. So now, in this picture, I mean, this thing over here, if instead of F, I have got X, okay? So whether I have X or X cross A1, I should get the same set, right? That is the idea. So if F is A1 fibrant, then, so what is F of Fx? Fx is supposed to be the morphisms from X to F, right? And F of X cross A1, these are the morphisms from X cross A1 to F. Now, if X and X cross A1, I mean, the projection map from X cross A1 to X is supposed to be an isomorphism, then this map from F of Fx to F of X cross A1 should be an isomorphism in the homotopy category of simplicial sets, which means that there should be a weak equivalence of simplicial sets. So this is one way of viewing what A1 fibrant means, that when an object is A1 fibrant, then it's not going to be able to distinguish between X and X cross A1, or X valued points and X cross A1 valued points, at least when you go down to the homotopy type. And in fact, so this is more generally, if I take any G, then the simplicial set of morphisms from G to F, this is weakly equivalent to the simplicial set of morphisms from G cross A1 to F. This is true for any G. Okay, so that's one way of understanding what A1 fibrant is supposed to do. So further, let us see what happens. So suppose F and G are two morphisms from a variety X into F, and suppose they are connected by an A1 homotopy. So again, I'm skipping the writing down an explicit definition of what I mean by A1 homotopy, but you know what it means, that basically there is a morphism from X cross A1 into F, such that if I restrict this to X cross 0, right, then I will get F. And if I restrict it to X cross 1, then I will get G. So this is what I mean as a A1 homotopy connect G. So now if F is A1 fibrant, then these elements F and G, they are supposed to be connected by a one simplex delta 1 inside the simplicial set Fx. Okay, so this is giving you a more I mean, the idea of this discussion is to give you some kind of an intuitive understanding, a geometric picture of what this A1 fibrant approximation functor is supposed to do, that it is replacing any A1 homotopy like this by a one simplex. Okay, so roughly speaking, and that I have deliberately underlined this twice because there is a lot of stuff to be filled in there, but roughly speaking, this is the intuition, that what LA1 does is that it takes a space F and it creates a new space out of it, such that the A1 homotopy, X cross A1 to F, this corresponds to a simplicial homotopy, X cross delta 1 to inside LA1 of F. Okay, so this is actually what it is. And in fact, if you look at the paper by Morel and Wojcicki, which, where this categories was properly constructed for the first time. So there, they actually give you an explicit construction of the LA1 functor. And I mean, it looks like a very complicated construction, but I mean, if you just remember that this is what it is supposed to do, then it becomes very transparent what they are trying to do. Of course, then it requires, they write down a formula and then one has to prove explicitly that this formula has all the required properties, which becomes a technical proof. But this is really the simple intuition behind what is attempted there, or well, what is done there actually. So now that we have, so if you, let's go back to our what we discussed in the last lecture. So for simplicial sets, we defined pi naught and pi i's, right? So one way, the way we did this was actually we took the geometric realization of a simplicial set and said that the homotopy groups of the simplicial set are the same as the homotopy groups of the associated topological space. So the reason why we have to do this is that, well, really, if you wanted to talk about, say, pi 1 of a simplicial set, what would you want to do? I mean, just if you were to try to replicate what you're doing in the context of topological spaces, what would you try to do? So if you take a topological space, what is its pi 1? So you look at maps from S1 into that, pointed maps, right? So you have a base point in S1, you fix a base point in your space, and you look at morphisms from S1 into that, and you want to look at homotopy classes of such maps. So if I try to replicate that in the category of simplicial sets, what will I do? Instead of S1, the topological space S1, I will have some simplicial set, whose geometric realization is S1. Right? I'll just pick a simplicial set equivalent of S1. And then I'll try to map this into my simplicial set X. But as I said, the morphisms from a simplicial set into any given simplicial set, in the homotopy category, they may form a much bigger set, unless your simplicial set happens to be a Kahn complex, right? If I want to look at maps from S1 into X, then to get a good picture of it, really, I need to replace X by its fibrant approximation. Okay, so that is actually what we do, that we replace X by its Kahn complex, and then we can look at morphisms from S1 into this Kahn complex, and then we can so whatever definition of pi 1 we have in algebraic topology, for topological spaces, we can actually imitate that entirely in the category of simplicial sets, and that you can get a completely combinatorial definition of what is pi 1 of a simplicial set without ever relying on the notion of geometric realization. So what we did for the geometric realization, that was just a shortcut to cut down on the discussion. But it makes sense to talk about this again, that whenever I'm talking about homotopy groups, what am I really looking at? I'm taking my space and I'm mapping spheres into it, right? And I try to understand what the collection of maps of spheres into my space, what does that look like? So if I want to do that, and I want to get a proper picture, which is going to really reflect what my model category is, then I should replace my space by an even fibrant approximation first. So that is what we do. So we first replace F, given simplicial space, given space F, by its A1 fibrant approximation LA1, and then we calculate its pi I sheaf. Okay, and then that is the A1 version of pi I. So for example, pi naught A1, this is the ordinary simplicial pi naught, which we just discussed earlier, of LA1 of F. And pi I of pi I A1 of F comma X naught, where X naught is some point over some scheme U. This is pi naught of LA1 F at the base point X naught. So, or rather the base point, which is the image of X naught, but I didn't write that in explicit detail. So the point is that just by replacing F by the A1 fibrant approximation, we are able to get A1 versions of all this data that we had created, the algebraic topology invariants that we had created earlier, just for the simplicial model structure. So now the thing is that the idea is that these functors pi naught A1 and pi I A1, they are supposed to capture the algebraic topology. So this is, I put this in quotes because it's a very, very loose and crude statement, but it's still, the idea is to I'm trying to be very, very informal just to convey the intuition that, in any space F. So, it's what is my space? My space is actually a simplicial sheaf over my base scheme, but I'm thinking of it as a space. Meaning what? So basically, I'm the points of the space are basically morphisms from any scheme into this, right? Into this sheet. So the points, the x-valued points of my space are basically the evaluation of this sheaf at x, right? And so I'm, for example, if I take, so if I look at x cross A1 and I evaluate f at x cross A1, what is that? You should view that as maps from x cross A1 into F. So you can view it as some kind of homotopy of X happening inside F. And so this is what I mean by a network of A1s in F. So what are all the A1 homotopies and all the maps from A1 parameterized by various spaces inside F? This is what I mean as the network of A1s. So the thing is that what we do here, as I said, wherever we have an A1 homotopy, we replace it by a simplicial homotopy. So wherever there is, you can view it like, visualize it like this, that inside X, there is a A1 running, and we somehow create a geometric object which takes that away and puts a delta 1 in its place, right? So when all this transformation is done, then you have a very big simplicial set, which is telling you how the A1s were distributed in the original space. And then we look at the algebraic topology of this, which will tell you how all those A1s were fitting together in your original space, right? That is the idea. So this is what I mean, that it captures the algebraic topology of the network of A1s inside F. Yeah, so I mean, this is such a crude description that it would offend an expert. So I'm just putting a disclaimer there that this is how this is very, very informal. So now a fact is, which is equivalent to, which is an analog of the fact that we saw earlier, that a morphism from F to G is an A1 equivalence if and only if it induces an isomorphism on the pi naught A1s and pi I A1s. So once again, these pi I A1s are the algebraic invariants that you can use to detect A1 equivalences, and they actually capture the A1 homotopy type of the space. So this is not a deep theorem, actually. It's just a formal consequence of the machinery that we have created. So now I'm just going to list out some interesting facts and some questions. Now these pi I A1s, these are A1 invariant for all I greater than 1. So what is A1 invariant? So a sheaf is A1 invariant if when you evaluate it on X, or you evaluate it on X cross A1, it is giving you the same thing. Okay. So what does this? What would be the analogous notion in the category of topological spaces? So in the category of topological spaces, instead of A1, what do I have? I have the unit interval delta 1, right? So I can say that a topological space X is delta 1 invariant if any morphism from say Y into X. If you consider morphisms from Y into X or morphisms from Y cross delta 1 into X, that's the same set. Now, in particular, you can take Y to be a point. So what we are saying is the morphisms from point into X is the same as morphisms from delta 1 into X. When does this happen? This happens only when your space is discrete. Right? It's just a bunch of points. There are no non-trivial maps from delta 1 into your space. So when you take a space and you calculate its pi i's, what do you get? You get, well, pi 0, you just get a set. So you can view the set as just a discrete topological space, right? It's and that's what it is. And similarly, the pi i's, they are also groups, but that just means it's a set with a group structure. But so again, it's a discrete topological space. So this is the analogous notion, analogous thing that is happening here, that for I greater than 1, these pi i's, they are actually A1 invariant. But for pi 0, this was a long-standing problem for a while, that there was a conjecture this might be A1 invariant, but quite recently, Ayub has given and shows that this is not A1 invariant in general. Pi naught is not A1 invariant, which is aesthetically, it is not very pleasing, but it is what it is. And maybe some constructions may need to be modified and so on, but it still actually makes it interesting that why is it not A1 invariant? So his example is of an abstract space. I mean, abstract in the sense that it is not a scheme. Okay, it's not a variety actually. So I would still be knowing if pi naught A1 is A1 invariant when X is a variety. This is still, I mean, it's an interesting problem. Okay, so let's, I mean, I'll come back to pi naught A1 again, but let's talk about something else. So in topology, one of the basic computations that one does with homotopy groups is this one, that the first things computation you see is that pi 1 of S1 is Z, right? This is the first thing that first theorem that you see. So, and then one can, push that result up into higher dimensions and show that pi n of Sn is also the group of isomorphic to the group of integers. So if you try to get an analogous result in A1 homotopy, so of course, what is the appropriate notion of sphere that you might want? So there are different notions of sphere, but I would say, okay, let's, I mean, just to show you one just to show you an analog of this result, let's look at An cross 0. So what is pi n Sn? I am looking at morph from Sn into Sn, right? And basically what we are saying is that these morphisms from Sn into Sn, their homotopy classes, they are characterized by an integer, which is called the degree of the map, right? So you have a similar thing over here, that you're looking at morphisms from An minus 0 to N minus 0, and you're looking at A1 homotopy classes of this. So these are given by, well, a different group. And so this is the notion of degree. This is the degree map in A1 homotopy. So what is this group? So this is the Grothendieck-Witt group of quadratic forms over K. So this is a very rich algebraic object which captures a lot of information about this this field K, right? So I mean, so primarily, I mean, you would call this a number theoretic object which represents, which captures some number theoretic properties of K. So this is the analog of so actually, yeah, what is K actually? So I should have said that I'm looking at varieties over K. That's what K is. So basically, A and K minus 0 to A and K minus 0. This is the Grothendieck-Witt group of quadratic forms over K. So this is the analog of Z in A1 homotopy. And so the thing is that you can actually build, basically the role of Z that Z plays in our older theories. Well, you can kind of replace, now you can make it a project of yours that you want to replace this Z by this Grothendieck-Witt group everywhere and see if you get what is the analog, the A1 homotopy analog of all your old constructions. So we have something called intersection theory and enumerative geometry. So where you say some varieties intersect in a point, and you figure out you define what is the intersection number at that point, and so on. So so this you can do, this game you can play with this Grothendieck-Witt group, and it gives you a refined version of intersection theory in which the role of Z is taken by this group. And this is a topic on which a lot of work has been done. So by Mark Levine and many other people. So you can take a look at this. So see references later, but so I've listed out some references later, but I have not written references for this. But I think if you just search Mark Levine's works and look up for refined enumerative geometry, you would find the appropriate paper. But so anyway, I'm not talking much about that, but let's carry on. And so just to comment that in general, for any space, x to calculate pi 0 x, pi 0 a1 of x or pi I a1 of x, this is a hard problem. And primarily the reason why it's a hard problem is because, well, you are taking a space and writing its A1 fibrant approximation. And the A1 fibrant approximation functor is, it's too complicated. It's impossible to do any real calculations with it. So that's why normally what people are doing is, I mean, you have to do calculations with some kind of a indirect technique. I mean, so meaning that basically what are the indirect techniques for calculating homotopy groups? So you take what is called a fibrant sequence, a fibration sequence of spaces, and corresponding to a fibration sequence, there is a long exact sequence of homotopy groups, and you basically use that to calculate various homotopy groups. So you are eventually restricted in what you can do, right? So, I mean, this is not just a problem in A1 homotopy. I guess it's also a problem in general, but A1 homotopy, it's a particularly hard problem. So this is roughly what we do. There is just like you have fibration sequence in topology, you have a notion of A1 fibration sequences, and you basically try to see where, and those are the situations where you can get some calculations. So results are available in special cases like for algebraic groups or homogeneous spaces and so on, but very little can be said so far in general. So pi i's in general are complicated, but let me talk about pi 0 again. So see, if you take any, see, when is its A1 homotopy, when is it going to be interesting from the point of view of A1 homotopy theory? So what is, you take your variety, and when you apply LA1 to that, what is it doing? Wherever you have a copy of A1, right, basically morphism from A1 into your variety, that is going to be replaced by a delta 1, right? That's the idea. And if you have a family, let's say you have got a family of A1s parameterized by A1s, then you might get a higher dimensional simplex, right, in LA1 of X. So the thing is that as long as your X has lots of copies of A1 in it, the A1 homotopy type will represent something interesting, because that's what it is supposed to measure. It's supposed to show you the algebraic topology of the network of A1s in your X, right? That's the slogan that I had talked about earlier. So varieties which don't admit any non-trivial maps from A1, they're not going to be interesting. So for example, if you abelian variety. So in an abelian variety, there are no non-trivial maps from A1 into the abelian variety. Any such map actually factors through a point. And so from the perspective of A1 homotopy theory, abelian varieties, which are actually, they seem like nice, they might look like nice irreducible varieties, but from the point of view of A1 homotopy theory, they are basically they are basically like discrete spaces, right? There is nothing to study there. They are like sets. So, but if you have a lot of rational curves, like for example, in a rational variety, or a nearly rational variety. So nearly rational means that basically property, I would say, so nearly rational properties are like being unirational. Unirational means that you admit a dominant map from N into your onto your variety, or suppose it's retract rational, which means that it contains an open subset, which is a retract of an open subset of Pn. So such things. So these are things which will not naturally have a lot of rational curves. So there, the A1 homotopy type is quite interesting, but it's not many results are known so far, except for a few. So for example, what is known is that retract rational is the same as being A1. Well, it implies being A1 connected. So A1 connectedness, but on the other hand, the converse is not known. What do I mean by being A1 connected? I mean that pi naught A1 is trivial. Okay, it's a point. So retract rationality implies A1 connected, but the converse is not true. Well, converse we don't know. We kind of hope that it might be true, because if it is true, then it will give us a very nice. It will give us some understanding of what connectedness is. In the context of varieties, so the thing is, of course, this is not going to be true in general, because if you take a general, see, for you, what you could do is you could just take a cone over any variety, right? So basically you take your variety and you connect it, you fix a point and you connect it with A1s, right? So an A1 cone over that. So that is going to be A1 connected for trivial reasons because everything is connected to a point, but then that's not smooth. So, but if you have a smooth variety, which happens to be A1 connected, then will it be a retract rational? So that seems, well, it's not known to be true. In fact, but it might be. I mean, so, but I mean, the thing is that so little is known that actually you don't even know whether, I mean, as far as I know, I don't think one knows that whether smooth A connected varieties are even unirational. It's much weaker than being retract rational. So the thing is that this is an open problem, and just understanding what kind of near rationality property A1 connectedness is, that is a very nice problem actually. And yeah, so okay, so that's it for those problems. But now let me come back to the Nisnevich topology, because one of my objectives for this talk was to give a little more clarity on why we are talking about the Nisnevich topology. So, so just recall that U to X is a Nisnevich cover if it's an Ethal cover, and for any point little x of X, it can be lifted to U. So the point X, what its residue field is kappa X. So it's a kappa X rational point. So in general, if you take an Ethal map like this, so sitting on over X is not necessarily a kappa X rational point, but a point whose residue field may be a separable, finite separable extension of kappa X, right? So the thing is that if you are actually able to lift X to a kappa X rational point for every X, then you say that this is a Nisnevich cover. The thing is that just to give you an understanding of what a strong condition this is, you could take X to be the generic point. So let's say X is irreducible, and you capital X is irreducible, and you take little x to be the generic point of capital X. Then if you are able to lift that, that really means that you're defining a rational map from X into U, which is a section of your given map, right? Which means actually that there is an open subset of, I mean, X and U have an isomorphic open subset, right? Which is a Zariski open subset. So which is a very strong condition. And so in that sense, this is kind of very close to the Zariski topology. Okay, it's now the Ethal topology doesn't do this at all, right? The Ethal topology is much more wide, but this is actually quite close to the Zariski topology. But at the same time, it is fine enough to admit some interesting properties that we would like to have, to do some interesting geometry, or really I should have said some interesting some interesting algebraic topology. So what does one mean by that? So in differential topology, so there is a familiar theorem that if you have a manifold and if Z is an embedded submanifold, so like for what you might imagine is like on the surface, you can take a smooth curve, right? On a smooth surface, you take a smooth curve. Then Z has a tubular neighborhood in X, which means that there is a neighborhood, an open neighborhood of Z, which is diffeomorphic to the normal bundle of Z in X. So I have drawn a crude picture that here I've got my space and like a surface, I've got a curve. Maybe I should have drawn the curve to be a little longer, but so you can take an open neighborhood. I mean, you can view it as some kind of a, so what will be the normal bundle look like? If this is a surface and this the submanifold is a curve, then the normal bundle is a line bundle, right? So you can see this little fattening as basically a space that is diffeomorphic or at least homeomorphic to the line bundle. So this is what one calls as a tubular neighborhood, which is a very useful concept. So there is no such thing in Zariski topology, right? Because Zariski topology is just very, very crude. So that is one reason why the Zariski topology would not be that useful if you wanted to do algebraic topology in that sense. I mean, the Nisnevich topology, this is almost true. So in what sense? So this is the so-called purity theorem of Morel and Voevodsky. So if Z is sitting inside X, this is a closed immersion of smooth varieties. So this is the analog of an embedding of a submanifold, then let n be the normal bundle of Z in X. So if you think about it intuitively, roughly it is like if you're sitting inside Z and you are looking in your immediate neighborhood, then the normal bundle is like a linear approximation of your space X, right? So close by, they should feel like the same. So what is, so inside N, what is the canonical copy of, inside N, what is the canonical copy of Z that is there? The zero section, right? It's a vector bundle, the Z over Z. The zero section is the copy of Z that we want to talk about. So then the theorem says that if you take X modulo X minus Z, so what does this mean? So you have got your space X. Inside this, there is this subspace X minus Z. Okay, and you take the quotient of one space by another. So this is no longer quotient in what sense? So quotient in the sense that a quotient in the sense of Nisnevich sheaves, right? So for any, if I take any sheaf and I take a subsheaf, then I can take the quotient, which will be a pre-sheaf, and then I can take the sheafification of that. So this is the quotient in the context of, in the category of sheaves. So this is just some very abstract Nisnevich sheaf. This is even equivalent to n modulo n minus the zero section. Okay, so this is, I mean, this doesn't sound like we talked about the tubular neighborhood at all, but if it comes quite close. So let me elaborate a little further. So roughly speaking, the idea is that this is supposed to give you an analog of excision in A1 homotopy. So the excision axiom that you have for homology or cohomology. So that is what you want to try to emulate. Like, for example, you have got X, and you inside X you have got a subspace A. Then what do we say? So if you look at the homology or cohomology of X comma A, well, you could remove whatever you want from A, and thus shrink the pair. This will still give you the same algebraic invariant. That's what we mean by excision. So this is something similar is happening over here, that we are saying that inside, if you're looking at the pair X minus X comma X minus Z, right? So then if you remove whatever you want from X minus Z, and until what is left is actually an infinitesimal version of X around Z, that is the same thing as n over n minus, doing the same thing with n. So this is roughly what it is saying, that it's basically giving us the right machinery to do excision. So the thing is that in the Nisnevich topology, the analog of a neighborhood is called is the henselization of X at Z. So it's I mean, I think you may have seen what is the henselization of a ring at some ideal. Right, so you may have seen the definition of a Henselian ring. So it's like a very small neighborhood. So it's not as fine a neighborhood as taking the completion of a ring at some ideal. It's a little bigger than that, but it's also finer than, for example, taking the localization of a ring at some prime ideal. So it sits somewhere in the middle. So the question I might ask is the henselization of X at Z, is this isomorphic to the henselization of N at sigma Z? So that seems reasonable, right? That locally, so what is the tubular neighborhood theorem saying? That near Z, X looks just like the normal bundle, right? So isn't this reasonable to say that if this were to happen in Nisnevich topology, you should say that near Z, X looks like what N looks like near section. So when I say near, I should take the henselization. So does the henselization of X at Z, does it look like the henselization of N at sigma at the zero section? So the thing is, well, this is actually probably not true globally, but locally it is true. So at any point of Z, if you look at it locally, it is true. The only problem is that these isomorphisms do not glue together properly. And so it probably doesn't hold globally. So I'm saying probably because, I mean, I was thinking about this, but I could never actually construct a counterexample. I think this is probably not going to hold globally. But what the purity theorem is saying is that, okay, I don't care about this. I mean, you don't need this to be exactly like that. You just need to do excision, and this is actually enough for excision. So that's roughly what it is saying. So so that is the upshot of this discussion was, so why Nisnevich topology? Because the Nisnevich topology is just fine enough to allow you to do excision, and at the same time it is close enough to the Zariski topology to be of, to have some of its, like for example, the Ithal topology will not be very sensitive to the residue field, but the Nisnevich topology will be a little more sensitive to residue fields. So that's roughly that's a rough explanation for why the Nisnevich topology is useful. Okay, so I'll just wrap up here. So the general philosophy of A1 homotopy is that, I mean, this is a very, very loose statement, but the idea is that you want to use LA1 functor to turn an algebraic geometry problem on X into an algebraic topology problem in LA1X. And then maybe you can use some algebraic machinery from algebraic topology to solve that problem, and then maybe go back. That is roughly the idea. That at least that's the ambition. And in some cases, this has worked out. Like for example, the notion of Euler classes for vector bundles. So there was a certain construction of inspired by Nori and worked out by Bhattodekar and Raja Sridharan. And so another construction was done by Baj and Morel using these ideas. So rather, they actually did this before their construction, before before the construction of the A1 homotopy model category, but it can be framed in that situation. So this philosophy has worked in some cases, is what all I will say. So I think I'm out of time, but if it's okay, I'll just quickly talk about some references. So I'll just take a couple of minutes. So the initial road, so this is just an initial roadmap to A1 homotopy theory. So I'm just saying something for people who are possibly new PhD students or pre-PhD students. So what do you need to read to make to get to a point where you are actually reading some of this literature? So firstly, you need to read algebraic geometry, which means that all the prerequisites of algebraic geometry also come in, which is commutative algebra and so on. But you should be able to at least get through Hartshorne's algebraic geometry, let's say the first 3 chapters. Maybe the 3rd chapter is not that essential, but at least you should be comfortable with the language. Now, this will not necessarily introduce you to Grothendieck topologies or Ithal maps, so that you can read up somewhere. So one good reference or standard reference is Mill's book on Ithal cohomology. The first 2 chapters should cover that. So once you have understood this much, then, well, of course, since the idea of A1 homotopy is to use the methods of algebraic topology in algebraic geometry, you should know the algebraic topology. Something like Hatcher's algebraic topology or anything equivalent, like for example, Spanier's book would be fine. But so you should have some of that. And then the theory of model categories, which is so that's like a more abstract version of the machinery that is developed in algebraic topology, that you need to read up to some level. So a book which I think is a very good book for as an introductory book is this book by Hartshorne. So, well, it's a new book as an introductory book because it sort of works everything out for you. It doesn't leave anything to exercises. There are no exercises in the book. Everything is worked out. And so you may or may not prefer that, but yeah, it does work everything out and explains everything in explicit detail. So I do like the book for that. But because of that, it's a big book. There is a shorter movie, which is also very nice. There is also a book which focuses on the simplicial homotopy theory by Gauss and Jardine. So any of these should be fine, but I think Herschel's book might be the easiest to read, or you can go and read Quillen's book also. That's a different matter. But anyway, so this is just one suggestion. And then once you have done all these things, then you can read Morel-Wojewski's paper, the foundational paper, A1 homotopy theory of schemes. But if you want a quick introduction for the subject, just a sort of an intuitive discussion, something like what we have been doing in these lectures. So you could look at Morel's book, A1 algebraic topology over a field, which is not an introductory book. It is not an easy book to read, but chapter 1 of this book can certainly be read to give you an overview of what the philosophy of the subject is. So that, I think that's enough to get you started. So yeah, that's where I stop.
Let us thank the speaker. Any questions? If not, we can thank the speaker again and end the session.
Hello. Hello.
Yeah. Is that a question?
Yeah, I had a question for the professor. Is it not possible?
Yeah. I don't know.
Hello.
Just a second.
Yeah. So I wanted to ask about the analog of excision that you talked about. Like, if we could go back, like, is
Yeah, sure.
there anyone?
Can you ask the question?
Yeah, sure. Like, I would like if the slides were being seen. So the question is, he was talking about the analogs of excision in, like, in the Nisnevich topology. I just wanted to hear that once more if possible. Like, I was not very clear.
Okay, so the point is that, I mean, if you recall what is excision in the context of algebraic topology, so what you have is, you're trying to attach invariants like homology or cohomology to pairs of spaces like x comma a, where a is a subspace of x.
Yeah. Yes.
And so the way it is, you are supposed to be really thinking about is that, when you're looking at the homology of x comma a, then if the pair is nice, this is like the reduced homology of x modulo a, right? When we're basically you're compressing a to a point.
Yeah.
And so what we are saying there is, what excision is doing is that it is saying that in place of x comma a, what I could do is remove a smaller a set b, which is already contained in a, right? I could get rid of it. So for example, if b is contained in a, then the homology x comma a is the same thing as the homology of x comma b, x minus b comma a minus b.
Yeah.
So this is what it means, that you're trying to compress something to a point within your space, and what excision is saying is that you can, I mean, the thing that is compressed, the geometry of that is not relevant. This is what excision says, that you can remove parts of that space which is being compressed. Anyway, it is going to get compressed, right? So what is happening inside that space should not matter so much. That is what excision is saying. So you want to do this purity theorem, it is an analog of that, in the sense that it is saying that if you're looking at a space X, and the role of A is being played by the complement of some submanifold or some smooth subvariety, then so you're looking at X modulo X minus Z. So roughly the idea is that this X, what is happening in X outside of Z is not relevant. What is really relevant is just an infinitesimal neighborhood of Z within X. So that is roughly the idea. So it is saying that, so it is taking this aspect of it, that this interpretation of excision, that if you're looking at X modulo X minus Z, then you should be able to replace X by some infinitesimal neighborhood of X around Z. And then it is taking the intuition of tubular neighborhoods, which is saying that infinitesimal neighborhood of X at Z should look like the infinitesimal neighborhood of the normal bundle at the zero section. And so that's why it's the final statement is that X modulo X minus Z, this is equal to N modulo N minus the zero section. So it's a bit of a long-winded analogy, but it is just right to allow you to do exigent type arguments in A1 homotopy proofs. That is
So the n is the normal bundle around the point that you're taking.
normal bundle around.
No, so you said x quotient x minus z is the same as n quotient by n minus the zero section, right?
Yeah.
So this n is the
N is the normal bundle of Z within X. So basically the bundle of vectors which are, orthogonal roughly to Z within
Okay.
X.
Okay. Okay. Thank you. Thank you.
Yeah, I'll end the meeting now.